Back in Chem 1A, we learned about the standard enthalpy change for a reaction. So that's delta H reaction, and the degree symbol here means it's standard. That's the change in enthalpy for a process where all the reactants and products are in their standard states. Some recollection of that? These are the definitions of the standard states. For a gas, it would be the pure gas at 1 atmosphere. For a liquid or solid, the pure substance in its most stable form at 1 atmosphere of pressure and the temperature of interest, which is usually 25 degrees Celsius. For a substance in solution, the concentration is 1 molar. Now, normally, things are not in their standard states, right? All the experiments we've done, the stuff has not been in their standard states. But you got to start somewhere, right? The standard entropy change has a similar definition. So the standard entropy change for a reaction is the change in entropy for a process in which all the reactants and products are in their standard states. So entropy is a state function, meaning it doesn't matter how you got from point A to point B, it's just the difference between them. And so we can say that the standard entropy change for the reaction is equal to the entropy of the products, the final state, minus the entropy of the reactants. So we need to define standard molar entropies. And so that's S with a degree symbol. For enthalpy, we had to pick a 0 because you can't calculate absolute values of enthalpy. It's a bit like elevation. Using the center of the Earth as 0 is not practical. But for entropy, there is an absolute 0. So this is the third law of thermodynamics. The entropy of a perfect crystal at absolute 0 is 0. So a perfect crystal where every single atom is in its place, W, the number of ways to arrange the components, equals 1. So based on Boltzmann's definition of entropy, where entropy is equal to K times the natural log of W, if W is 1, the log of 1 is 0, and entropy is 0. And it kind of makes intuitive sense too. It's like, okay, this perfect crystal is perfectly ordered, right? And the particles they're not even vibrating at 0 Kelvin, right? All movement stops. So they're perfectly still and they're perfectly arranged. 0 entropy, okay? Entropy is an extensive property, just like enthalpy. It depends on the amount of substance. So when you talk about enthalpy, the example in 1A a lot of times was burning octane, right, in gasoline. So you burn a little bit of gasoline or you burn a lot of gasoline. Does that change the amount of heat that you give out? Yeah, right? Couple drops of gasoline burning on the counter, no big deal. Couple gallons of gasoline spilled and burning, okay, that's not going to be good, right? Depends on the amount of stuff. Entropy also depends on the amount of stuff. So when we look up entropies, they're going to be molar entropies, so joules per mole Kelvin. And this is an abbreviated table. It's in the chapter. That appendix in the back has an extensive list of delta H's and delta S's. So we see that even the elements in their standard states, none of these have 0 entropy. All those entropies are positive. So at 25 degrees Celsius, the standard entropy of any substance is the energy dispersed into 1 mole of that substance. And what the value of that entropy is depends on the number of places that you can put the energy or the number of ways that you can arrange the energy. How dispersed the energy is, it's kind of hard to put that exactly into words. But the entropy is affected by the state of the substance, its molar mass, the particular allotrope, molar complexity, and extent of dissolution. And so we'll talk about each of those separately. So the state of the substance. The entropy of a gas is generally larger than the entropy of a liquid. Liquid has more entropy than a solid, because gases have more energetically equivalent ways to arrange their components. In a solid, the particles are stuck relative to each other, and they can vibrate at different rates, but they can't move around, and so there's fewer ways to arrange them. So if we see water as a liquid, entropy is 70 joules per mole Kelvin. As a gas, it's significantly higher, 188. Standard molar entropy depends on the molar mass of the substance. And the exact reasoning for this, as it says in the book, is beyond the scope of the book, meaning we don't want to go there. And we don't need to, so that's good, right? But if we look at the noble gases, and when you're comparing these things, like if you're looking at different states, you have to be comparing the same compound, right? If we're looking at molar mass, we need to have substances that are similar to each other. So here we've got the noble gases, and we're looking at the entropy relative to their size. So we see that as the atoms get larger, the entropy gets larger. So energy states associated with the motion of heavy atoms are more closely spaced, which allows for more dispersal of energy. I don't think that's really a very helpful sentence, but there it is. So bigger things will have more entropy. The allotrope. In case you forgot, allotrope is the form of an element. So some elements can exist in different forms as elements. Carbon is one of these. The commonly known allotropes are diamond and graphite. They are both pure carbon. So which allotrope you're talking about affects the entropy. So in a diamond, we have carbon atoms, but they're covalently bonded to each other in a three-dimensional structure. They cannot move relative to each other at all. In graphite, we have two-dimensional sheets of carbon atoms that are bonded to each other, and these sheets are held together by intermolecular forces, and they can slide relative to each other. And so the graphite has more entropy than the diamond does, because it is less constrained. Any questions yet? Molar complexity. There probably will be an exam question like this. Okay. So for a given state of matter, entropy generally increases with increasing molecular complexity. You think of that as there's more places to put the energy. So if we compare argon and nitrogen monoxide, both of them in the gas state, their molar masses are pretty similar, so we're not going to attribute this difference to a difference in molar mass. It's because the NO molecule is more complicated. So that argon atom has translational motion. It moves through space. Well, the NO molecule also has translational motion. It can move through space. But in addition to that, it has rotational motion. It can spin, and vibrational motion, where that bond can stretch and shrink. And so it can vibrate in itself like that. And so there's more ways that it can move, and so it has higher entropy. Any questions? Some more examples. Here looking at carbon monoxide and ethene, C2H4. Molar mass, almost identical. But C2H4 has a higher molar mass because it's more complex. How can we tell that it's more complex? It's got more atoms in it, right? So carbon monoxide has one bond between carbon and oxygen. If I remember correctly, it's a triple bond, but still, it's just the one connection between two atoms. Where here we have a lot of different bonds, and so each of those can have vibrational motion, and that adds to the entropy. If molar mass and complexity are increasing, then of course the molar entropy also increases. So here we're adding oxygen and nitrogen atoms to these. They get larger, but they also get more complicated. Dissolution. If we take a crystalline solid and we dissolve it into solution, the entropy will increase. What's happening here is the energy that was concentrated in the crystal. Now as the ions become solvated and start moving around, their energy becomes distributed throughout the whole solution. And so energy has spread out. That means entropy has increased. So same compound here, potassium chlorate as a solid, 143, in an aqueous solution, 265. Well, how can we calculate the standard entropy change for a reaction? We're going to do it just like we did with standard enthalpies. So we're going to subtract the entropies of the reactants, taking into account how many moles of them there are, from the standard entropies of the products. So this is the products minus the reactants. The N here represents the coefficients in the balanced chemical equation, because that standard entropy is so many joules per mole degree Kelvin, and we're multiplying by the number of moles in the reaction. And what we're calculating here, standard entropy of the reaction, is for molar quantities of the equation as written. So we need to remember that standard entropies are always non-zero at 25 degrees Celsius. For the enthalpies, elements in their standard states were zero. But here, nothing is zero. Okay, so it says calculate the standard entropy change for this reaction. So I'm going to look at the entropy that it has at the end, and I'm going to subtract the entropy that it has at the beginning. So remember, delta almost always means final minus initial. This is the final part, and this is the initial part. So here, I made a table with the values that we're going to need, so we don't have to scramble around and look for those. So the standard entropy for this reaction, standard entropy change, is going to be the standard entropies of the products. So we have 2 moles of water. 2 moles of water times the entropy for water, 188.8 joules per mole Kelvin, plus the other product, 2 moles of that, times its standard entropy, 248.2 joules per mole Kelvin, And then we're going to subtract the entropies of the reactants. So we have 2 moles of the H2S, 205.8 joules per mole Kelvin, plus 3 moles of oxygen, times its molar entropy, 205.2 joules per mole Kelvin. Normally when we do this calculation, we don't write out all these units, but I did it here because I want you to see the moles are canceling out. And so the units are working just like they're supposed to. When we're subtracting a bunch of stuff, you need to be a little careful in your calculator. It's not a bad idea to just use parentheses here so that you don't forget to subtract here as well. So I'm just going to do 2 times 188.8 plus 2 times 248.2 minus, open parentheses, 2 times 205.8 plus 3 times 205.2, close parentheses, negative 153.2 joules per Kelvin. Any questions? Got it right. Okay, so, this equation here looks a little intimidating, right? And you're like, well, I don't know if I can remember that, or even if I was given it, do I remember what it means, right? It's the delta S. It's the change in S. You take the S's of the final things, and you subtract the S's of the initial things. And we do that for delta H as well, and we're going to do it for delta G. So it's just this one idea that we can use for 3 different things.